Hello, good morning to all. Hello, can you hear me?
Yes,
Yes,
sir.
sir. Good morning, sir.
Very good morning, very good morning. Okay, so good morning to all. How are you all? Edric, how are you?
Uh, Good, sir.
How much good?
So good.
So good. That's great, that's great.
Sir,
Okay, yes.
okay, sir. Mm, did you correct my math and science TMA?
Yeah, I saw now. I told it perfect.
You corrected both of them.
Yes. I check both of them. It is perfect. There is no problem in that.
Both of them are correct now?
Yes.
Okay,
Yes.
got it.
What is that? Okay, we were doing chapter number 17.
Wait, yeah, sir, ma'am.
Sir, today I won't be attending SST class.
Okay, okay. Okay.
Yeah.
Okay, guys. So, good morning to all. One more time, I request David to turn on a camera. Rest, they are joining. So, we were doing electric generator. I mean, we learned about AC and DC. And for the revision, if I will tell it to you, what do you mean by DC? DC is a direct current in which the current flows in only one direction. Did you understand?
Sir,
And when we learn about AC, AC is a alternating current in which the current moves up, then down, then up, then down, then up, then down. Means the direction change periodically. Okay. Now we learned about the frequency also. Like if you check it, that our house light, the tube light, they flicker, but they flicker so fastly that it looks like that the light is constant. But basically, if you will take your mobile and if you will use slow motion video, then you will find it out the light is flickering, like tuck 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 tuck, on off on off on off on off. Did you understand, guys? Yes. So this is how it done. Yes, Cedric.
sir,
Yes.
okay. So basically, no, in the AC generator, the current will like flow from like first zero, then up, then zero, then down, then zero. But in DC, no, that day you said that goes in a straight line. Sir, it does not. It bounces like this, then it touches zero, then it again bounces up, it touches zero, then again bounces up and touches zero. It's like that. It does not always straight. It like bounces, touches zero, but never goes below zero.
No, it won't go to zero. DC doesn't go to zero. The DC never goes. If it will go to zero, then it means that we have a chance to get out of it. DC. It may be in the oscillation form, like it can be in the graph on the fun phase only. Then it can make this type, but it don't does not touch to zero.
Okay, like just little above zero then. Little above zero.
Yeah. So there won't be any chance for getting out of the, like, that's why DC is very fatal. Did you understand?
Yes, sir.
Mm. Okay, so now we will learn about AC generator, and we will learn about AC generator function. Okay, so we were doing. I'll first show you the video, then we will understand
D
it very deeply.
DC. Yeah. AC DC.
So I told you that the when the coil moves in the magnetic field, it generated electricity. Yes or no? When
Yes, sir.
coil moved in the magnetic field, it generated electricity. So now we will learn about this only with the help of this Khan Academy, India. I believe it should be in English.
Khan Academy. Khan Academy or An Academy?
Khan Academy. Hmm? Hmm. Give me a second.
How do power stations provide electricity to
Okay, who joined? Miracle joined. Okay. So, can you see this picture?
Yes, sir.
Yes. Okay, so now I will start this video.
Thousands of houses around a city. They don't use giant batteries. They do that by spinning a giant turbine like this. And to spin such a turbine, some power stations use very hot steam that blows over the turbines and spins it. Or maybe we can use the energy of the falling water. Or another example could be we fit these inside giant windmills and let the wind do the work for us. Whichever way you choose, all we do is spin a giant turbine. But how does turning something create electricity? Well, the technology is based on electromagnetic induction, discovered by Michael Faraday more than 200 years ago. The basic idea is that if you take a wire and move it up or down inside a magnetic field, it induces an electric current. So all we have to do is attach a coil of wire to these giant turbines and place them inside a magnetic field. As the turbine rotates, the coil starts rotating and the wires start moving up and down inside the magnetic field. That produces the electric current. And this can now be used to light up things. These devices are called electric generators. They convert spinning or mechanical energy into electrical energy. So let's look at them in detail now. So let's start by figuring out in what direction a current gets induced or generated in this coil once it starts rotating. So let's say, in our example, the coil rotates clockwise, somewhat like this. Now, how do we figure out the direction of the induced current? Well, we have already learned something called the Fleming's right-hand generator rule, which says you stretch the fingers of your right hand like this such that they are perpendicular to each other. Then the thumb represents the direction of the motion of the wire. That is the direction in which you're pushing the wire. The forefinger gives us the direction of the magnetic field. Then our middle finger will give us the direction of the current. So all we have to do is align our right hand to make sure the thumb and the forefinger point in the direction of the motion and the magnetic field. Then the middle finger will give us the direction of the current. So let's use our right hand rule on the pink wire that is going upwards, as you can see, and on the blue wire that is moving downwards.
Sir.
So it'll be a great idea if you can first see whether you can try it yourself.
Sir, I have a doubt, sir.
Yes. Yes.
Okay.
Yes.
So Fleming's right hand rule, why does it say you have to use your right hand to do this Kathakali dance? But that day you said
Because
left hand. That day
yeah.
you said left hand.
See, this is called as Fleming right hand rule for generator. It is saying for generator. Means in generator, when we have to find the direction of current with the help of magnetic field and the force, we use this point. Yes, Agatha.
But isn't Fleming's left-hand rule also the same, also used for the same purpose?
The Fleming left hand rule we use when a object or conductor having a electricity when it is placed in external magnetic field. Now here the conductor doesn't have electricity. Okay, it should be the electricity should be induced into it. Okay, when the force is there as well as the magnetic field is there. Did you understand? The Fleming left-hand rule and the generator rule is both are different. Okay, in generator we use Fleming right-hand rule for generator, but in normal use, when there is no production of electricity is there in normal cause, we use left-hand rule.
Okay, so here it is electromagnetic induction. No, so when electromagnetic induction is there, we use right hand rule.
Yes, right-hand rule.
But okay, so right hand rule and left hand rule both are same.
No, they both are different.
Okay, they are same, but we use them in different purposes.
Different purposes. Perfect.
Okay, and
So huh?
and same thing in left hand rule, thumb is force, index is magnetic field, and middle is current.
Middle finger is
Correct.
correct.
Same thing in right hand rule also. Thumb is force, middle is index is magnetic field, and middle is current.
Yes.
Oh.
So what we learn that there is a magnetic field which is moving from north to south direction, and in that magnetic field, when electric current is formed, then what happens? The current is induced inside the coil, and when the current is induced, we are using this. So the generator, what is the role of generator? We put petrol in it. We start the generator. So what generator will do? Generator will move this shaft, this coil. No, this coil will move towards this. Okay, this coil will move towards this like this with the help of generator, and because of that, the coil will generate electricity because it's in the presence of magnetic field. Yes or no? So
Yes.
this is how we get the AC generator. So we'll move forward to the next
So
part.
go ahead and use your right hand and see if you can figure out the direction of the current in the pink and the blue wire. Alright, if you've done it, let's first start with the pink wire. Because the pink wire is going up, the thumb should be pointing upwards. The magnetic field is to the right, so the forefinger should be pointing to the right. And so if we align our fingers that way, it will look like this. Since the middle finger is pointing inwards, this means the current in the pink wire must be inwards. Similarly, for the blue wire is moving downwards. So the thumb will be pointing down, the forefinger will still be pointing to the right. And so if we arrange our right hand over here, it will look like this. The middle finger is pointing out of the screen. That means the current in the blue wire will be coming out of the screen. So what we have seen is if a wire is moving upwards over here, then the current will be into the screen. And if the wire is moving downwards, then the current will be out of the screen. Remember this will be important. So now let's get rid of the hands and put arrow marks to indicate the current. And now we can guess what direction the current will be in the rest of the wires. Since the current has to flow from the pink to the blue, we can say that the current has to move here like this. And then the current has to move here this way. It goes out. It goes to that external circuit, maybe where there's a bulb. We'll look at that later. Then the current comes back like this and it flows in this way. And the current continues to flow like this as the coil keeps rotating. Because you can see the pink wire is still going up and the blue wire is still going down. Until we come to this point. Because now the pink wire starts moving downwards. And now the blue wire starts moving upwards. Can you see that? Again, if I go back and come back again, notice the pink wire is coming down and the blue wire is going up.
But in the previous frame, no, only the pink wire was shown. That means the pink wire was up and the blue wire was down.
So yeah, perfect. So in this, now everyone please pay attention. In this, we can check that with the help of Fleming right hand thumb rule, we got that the current is moving. Where's the pen? Yeah. So here we saw that current is moving in this direction, okay? Because Fleming right hand thumb rule, if we will apply, then the force is going towards up, magnetic field is towards downward. Okay.
No, magnetic field is towards the right. Magnetic field is towards the right, yeah. And current will flow this
towards. So like this, it will form, which is towards the coil. Yes. Yeah. But now when the shaft is moving like this, now the direction will change. Okay, how? Like if I will move in this direction, yeah. Now in the blue wire, which was current was going in this direction, now it moves towards the upward direction. So what happened, basically, what happened if I will make a graph of this? Okay. So like in the pink wire, first the current was going like this, then it becomes zero, then it goes to the next direction, then like this. So you can see the graph is formed like this. That's why it is called as AC current. Did you understand? The current is changing because the shaft is moving like this. Did you understand, Agatha? Edric, David? No. Okay. See, basically what happened. Hmm. First, we'll check this diagram. Okay. Now, Agatha, the current is moving towards the this. I'll put a mark. This is A, this is B, this is C, and this is D. Now the current is moving towards A direction. Yes? Yes or no? Okay. Now the current is moving towards A direction. So if I will put my hand like this, it is going towards A direction. So in pink one, the current is going towards D to A.
Yeah, like this, like this. So like this.
Yeah. And in blue one, the current is moving towards
B to
B to C.
like this, like
B
this,
to C.
like this.
Okay? Yeah. Perfect. Did you understand, guys? Any problem in that?
Yes, sir.
No. Okay. Now, when the shaft will rotate, so for example, this was like this. Now, when if it is rotate like this, now this blue, this is for example, this is blue one and this is pink one. Okay. For example, everyone see my this thing. Okay. This is blue one, this is pink one, and this is blue one. Okay. Now the current is moving here, and from this it is coming from here. Now, if it is moved like this, now this is blue one and it is going towards upward direction. Yes.
Yes, sir.
So if blue is going towards upward direction, so the current will be in the blue will be like this. Means the current which was going from B to C, now it changes towards to C to B. Did you understand, Agatha? No.
Like when this thing rotates, like when BC comes to the AD place, it will go from
Yes.
BC to CB.
Yes, from C to B. Means the current direction changes periodically. Did you understand?
Will also this pink also will change from DA
Yes.
to AD.
From pink it's also changes from A to D to D to A. It will change to A to D. It means that the current is changing periodically like this. Miracle, did you understand, beta? Are you there?
Yeah, sir, I'm here.
Okay. Did you understand what we are trying to say?
Yeah, sir.
So, for example, before, like when the current, like if I will take the AD conductor, so first it was going to this direction from A to D, so D to A. Then after like rotating, it become D to A, so it become negative to positive like that. Then again D to A, then A to D, D to A, then A to D. Like this, we are getting the graph. Okay, hence it is a AC current. And when you will observe this, where is this point?
Sir, so current keeps changing from D to A and CB.
A to D.
Oh, A to D. Okay, sir.
This one. One frame forward. One frame back.
No. I am not checking this. I am taking that part.
Yeah.
Where is that one? No, I'm not. So, for example, if the shaft is like this, I'm sorry. I'm very bad knowing. Means basically what I'm trying to say, for example, right now the shaft is like this. It moving towards upward direction. Now the shaft become like this. In this case, the current will be zero. Why? Because basically I told you in our like when we make this, so we have this force is current. This is magnetic field. This is current. Okay. In this case, everything should be 90 degree to each other. Yes. But now when it is like this, there is no 90 degrees form. Hence, the position of the shaft, if it is like this, there is no current is formed. That's why it becomes zero at this point. So what does this mean? When this pink part is going up, and become not become 90 degree, then it become like this. Now the blue part is going up, then again become like straight. Then the pink part is going up, then become it again like this. Then blue part is going up like this. At like this, the formation of current is there. Did you understand, guys?
Yes, sir.
David, are you there? Miracle?
Yes, sir. Yes, sir.
David, did you understand? No.
Yes.
Okay. Okay. So we'll go forward.
Because you can see the pink wire is still going up and the blue wire is still going down until we come to this point. Because now the pink wire starts moving downwards and now the blue wire starts moving upwards. Can you see that? Again, if I go back and come back again, notice the pink wire is coming down and because now the pink wire starts moving downwards and now the blue wire starts moving upwards. Can you see that? Again, if I go back and
Yeah. Here now only pink is seen and blue is at the down. No?
So in this condition, guys, the current will be zero. There won't be any production. That's why the graph is going like this, zero. Then now it become negative, and like this, the curve is.
Wait.
Did you listen, guys?
Wait, this is not zero. This is positive, I think. This is a full. This is
No. It become like, for example, what I will say, the force, like in this case, what is not perpendicular? The magnetic field is this direction. Now the force is upward direction. Okay, we'll see that video first.
come back again. Notice the pink wire is coming down and the blue wire is going up. This means now the current in the pink wire should be out of the screen because we already saw using our right hand rule. When the wire is going down, the current must be out. And in the blue wire, which is going up, the current must now be inwards. In other words, the current will now change its direction. This is the important thing. So the current changes its direction and it continues to flow this way until again the pink wire comes on the left side. Because now again, the pink wire starts going up, the blue wire starts going down, and as a result, the current in the pink wire will be inwards, the current in the blue wire will now be outwards, the current will again reverse. So every time our coil is in this position, which is perpendicular to the magnetic field, we will see that the current direction will flip. And so if you look at the entire animation now, it looks somewhat like this. Every time the coil comes in this position, perpendicular to the magnetic field, the current direction keeps changing. Now, of course, in the animation, I'm pausing the animation when my coil is perpendicular to the magnetic field so that we can see the current flipping its direction. But of course, in reality, the coil will be pushed continuously. There'll be no stopping. There'll be no jerking motion like we are seeing over here. Now, the next question we might have is how do we connect this coil to an external circuit, like say to a bulb? Well, we could connect it directly, right? Well, let's see what happens if we connect the circuit directly. Current will flow, no problem. But as the coil starts rotating, notice the wires start twisting and tangling and turning and whatnot. So that's going to be a problem. So to avoid that, we will not connect the wires directly. Instead, we will use an arrangement involving brushes and slip rings. It looks somewhat like this. So basically we have two metallic rings, the pink one and a blue one. And what you may not make out from my diagram over here is that each ring is connected to one wire only. So the pink ring is only connected to the left wire, and the blue ring is only connected to the right wire. And these wires are connected to carbon brushes, which is also conducting, and they are just touching these rings so that there is a metallic contact, but they're not stuck to it. So right now there is a contact, the circuit is complete, and as a result, the current comes out of the blue ring, as you can see, moves this way, and current flows into the pink ring and goes like this. And when the coil starts rotating, as you can see, the rings rotate along with the coil. But since the brushes are not stuck to the rings just slip through the brushes. That's why they're called as slip rings. As a result, the brushes will not rotate. That solves the problem of wires twisting and tangling, and all the while an electric contact is maintained. Now, once our coil comes in this position, we have seen that the current reverses. So now the current will flow out of the pink ring, goes like this through the bulb, and now enters into the blue ring. So for every half a rotation, the current through the bulb also reverses. Let's say when the current is flowing this way, the bulb glows blue. And let's say when the current reverses and flows like this, the bulb will glow yellow. And so now if you look at the entire animation, it looks somewhat like this. And so we have successfully built our generator. And what's interesting to see is that the current from that generator is continuously changing its direction. Such a current is called alternating current, or AC. And this might sound a little weird, but it turns out that when you want to transmit electricity over a long distance, like from the power station to your houses, then alternating currents, or AC, have some great advantages over unidirectional currents, or DC. And it's for that reason the current that we get at our houses, the electricity that we get at our houses, are all AC. And these generators are called AC generators. Finally, what if we want to build a DC generator, where we don't want the current direction to change? We want it to remain the same throughout.
Sir,
Yes, Agatha.
do you remember in Christmas we would put some Christmas lights and the lights will like blink and then change their color light?
That thing.
Yeah.
That thing, I believe it's not related to this, because in that, when you plug it into the house socket, there is one, like what is it? In Hindi, we say dibbi. In English, like what's a box? The box is there to change that point. Like if you will press the button in that box, then the light will change, or the jham jham or tum tum like that will come. Yeah. So I guess the box has a circuit, and in that circuit, because of that circuit is there, that's why the light is changing. Now, what is there in the box? I guess the box has a microchip controller, we can say. Like a box also has that computer, which is changing according to what we are doing. Yes. So that is why the light is changing and doing some dance in the light, in that light series. But that is not reason that AC is there. Okay. Like our mobile charger is also DC charger. It's not AC charger. Okay. Our mobile charger is also DC charger. Yeah.
Let's say in this direction. How do we do that?
So yeah. Where were we? Yeah. So did you understand the AC generator, David? Miracle? Agatha? Are you there? Miracle? Turn on the camera,
Yes, sir.
please. Yeah, Ira. Did you understand, beta? Yes.
So
Yes, Miracle.
So
Yes, Ira.
my camera is not working, so can't turn video.
so does it
Okay.
matter, like the thing that you spin, what is it called? Like that
The
generates the electricity. Does it matter
coil.
how fast? Yeah, does it matter how fast it's going? Like, will that affect the current that's coming? Like if it's spinning
Oh.
really slowly, will like current still be generated?
Yeah, current will be there. Current will be there. But I believe the oscillation which is created, like I told you the oscillation, no? For example, where is that? For example, the oscillation, like for example, if it is slow, like if it is fast, then it is creating 1, 2, 3, 4. 1, 2, 3 oscillation per second. For example, if it is very fast. And if it is very slow, then the light will, first of all, the oscillation will be less, the crest and the trough will be less, means the less light will generate. Less light will generate means the brightness of the light will decreases.
Okay, sir.
Like the tube light, which used to give very bright light, that brightness will be less because the generator, the coil speed is very less.
Okay, sir.
Did you understand, Agatha? David? David, do you have any doubt?
No.
No? Okay, now
So
AC generator is, yeah, Agatha.
when the current switch, when the current, okay, it is when the current switch that we are seeing the flickering of the light, right?
Yeah, basically, the flickering happens like this. The light is there, off, on, off, on, off, on, off, on, off, on, like that it's flicker. So in 1 second, because it's 150 times on and off, that's why we don't feel any difference, and the light behaves like that. Did you understand, guys? Yes or no? Okay.
Sir,
Yeah.
and if you're able to see that it is turning on and off and on and off, that means the voltage is very less.
Yes. Perfecto. Okay, so now we will read this electromagnetic generator. So I request Mr. David, please read this from here.
AC generators operate on the principle of electromagnetic induction. Alternating voltage or current may be generated by rotating a coil in the magnetic field or by rotating a magnetic field with a stationary coil. The value of the voltage or current generated depends on the number of turns in the coil, strength of the field, the speed at which the coil or magnetic field rotates.
So this is the direct answer of the IRA, that if the speed is less, then the voltage generated is very less, hence the current will flow very less, hence the bulb or the brightness will be very less. Did you understand? Agatha, David, Jashon, did you understand anything? Yes, Jashon, ask me. You got it? Miraculin, did you understand, beta? Any problem, ask me, beta.
No, sir, I understood.
Okay. Now, because the diagram is very important, as well as the question they used to ask, right? The working principle of the AC generator in 5 marks. So you guys have to learn this because this is very important. That's why I'm taking time and I'm spending on videos, so that, like, if I will tell you just right now like this only, na, then you will not get anything. But because of the animation, we are able to understand it. In future, we will make our own animation. Right now, we are using another one. It's okay. Did you understand, guys? Okay. Yes, David. Go on.
The structure of an AC generator has been shown in figure 17.3. Here, north and south is a strong permanent magnet. ABCD is a non-conductor frame on which copper wire has been coiled several times to form a rectangular coil. The coil is coated with a non-conductor substance like varnish so that they do not touch each other. This coil can freely move between north and south poles. This rectangular coil is made to rotate between two rings E and F. There are two contact brushes G and H attached to the rings respectively.
Sir. Sir.
Give me a second. Give me a second.
Agatha, I won't be coming for SST class today, okay? But I'll be coming tomorrow.
Okay. You did the homework, right?
Yeah, mostly.
Hello. Yeah, you guys take 4 minutes break, then come back. We will have class. Come back. 4 minutes. Okay, guys, come back, come back. Guys, come back. Agatha, Ira, David, Edric, Tishron, Miracle. Everyone come back. Come back, come back, come back. Hello, hello. Perfecto, perfect, perfect, perfect.
Yes.
Edric, come back, come back. David, come back. Ira, come back. David, yes, Mr. David, please, can you read this? Mr. David. David. Daud. He didn't came back. Yes. Then Jashan, please read this.
Sir?
Yeah, you read this, the structure of the AC generator.
The structure of an AC generator has been shown in figure 17.13. Here, north to south is a strong permanent magnet. ABCD is a non-conductor frame on which copper wire has been coiled several times to form a rectangular coil. The coil is coated with a non-conductor substance like varnish so that they do not touch each other. This coil can move freely between the north-south poles. This rectangular coil is made to rotate between two rings E and F. There are two contact brushes, G and H, attached to the rings respectively.
Yeah.
The rectangular frame ABCD moves between the north to south poles due to mechanical energy. Assume that the plane of the coil in that of the magnet lines of force and the
Coil
coil
starts moving.
moving in an anti-clockwise direction. The magnetic field entering into the phase ABCD of the coil increases from 0 to some infinite value and continues to increase until the coil becomes normal to the field. The rate at which the magnetic field light with coil charges is the maximum in the beginning and then it decreases continuously. Thus, the induced current in the coil is maximum at time t equals 0 and decrease passing time. When the coil
It means that, everyone please pay attention, it means that when the magnetic field is moving, then it is like that at peak, then it reduces to 0, then becomes 0, then at peak downwards direction, then reduces to 0, then 0, then increases at the upward direction, then reduces to 0. So this is how the current flows in AC generator. Agatha, David, did you understand? No.
Then, sir, no doubt, sir.
No doubt?
I
Yeah.
have.
Oh, you have doubt. Yes, please.
Sir. So basically, how come permanent magnet is there? How come there are two permanent magnets, that NS, north, south? What is that permanent magnet, sir? Why there are two?
Permanent magnet is there. This is one magnet, like two magnets are there. The one magnet has north direction towards the south direction, so that the magnetic field can be produced like this. Did you understand? No.
So like the magnetic field moves from like north to south, no? So like
Yeah.
I mean the direction will be from like this north, no? The down one to the up one.
Yeah. You got it? No.
Yes, sir. Well, no.
Perfecto. Then read this. Yeah. Jashan.
When the coil becomes normal to the field at the rate at which the magnetic flux of force charges becomes 0, and hence
the current becomes 0. So what is the normal means? Like for example, this is the normal condition. It's moving, and become like this. The magnetic field is like this, and the coil become like this. At that point, the answer will be 0. Then become negative, and then like this, it becomes 0 again. Okay, then become positive, then towards negative, positive, 0. Negative, positive, 0. Ouch. My hand locked like this. Okay. So did you understand, David? No, you didn't understand anything.
I understood.
Okay. Perfect. Yeah. Agatha, can you read the next paragraph, please?
When the coil further rotates, the face of the coil through which magnetic field enters start changing the direction of current reverse. It keeps increasing till the plane of the coil does not become parallel to the magnetic field lines. Thus, maximum current flows through the coil at this juncture. If the coil is rotated further, the area in contact
Yeah.
the area in
Oh,
contact
sorry, sir. Sorry. The area in contact then?
the area in contact with DCBA increase and the rate of change of magnetic field area becomes less. Thus, the amount of current flowing through the coil decreases. When the coil is perpendicular to the magnetic lines of force, then current becomes zero. Now the north pole of the magnet is reversed. Current starts flowing from its original direction of current produced, and its resultant keeps changing with time. Figure 17.14 shows the positions of coil at different stages and the current in the coil at these instants.
फोन हीट हो रहा है मेरा फोन हीट हो रहा है आप एक बार 600 रुपए कर दो क्यूआर पेमेंट वो कर रहे बार वो बारकोड आपको भेज रहे हैं आप एक बार पेमेंट कर देना मेरा फोन हीट अप हो रहा है हेलो या so where were we can you read this again with DCBA
With DCBA increase and the rate of change of magnetic field
Agatha
area,
are you there
yeah, I'm here. Oh, I'm here.
we can't hear your voice is it me only or is it everyone
No, it's only I can hear Agatha.
oh.
I can also hear her.
Me only hello can you hear me
Yeah.
okay yeah Agatha with DCBA sorry my phone is heating okay say it again with DCBA increase
With DCBA increase and the rate of change of magnetic field area becomes less, thus the amount of current flowing through the coil decreases. When the coil is perpendicular to the magnetic lines of force, then current becomes zero. Now the north pole of the magnet is reversed. Current starts flowing from its original direction. The direction of current produced and its resultant keeps changing with time. Figure 17.14 shows the position of the coils at different stages and the current in the coil at these instants.
so you guys can check this that when it is like this it is maximum current when it is removed when it is rotating so when it is parallel to the magnetic field line then it is maximum when it becomes perpendicular to the magnetic field line it becomes zero then again parallel because the direction change like AB like it was like this ADCB now it become DCBA means that the direction change become maximum at the downward direction then zero so like this it happens did you understand guys
Yes, sir.
yes or no so alternating current doesn't start from zero because it is maximum in this position this is maximum when it starts moving this is maximum at zero position then it becomes zero then negative zero negative maximum then zero then positive maximum zero negative maximum zero positive maximum zero like this it moves did you understand David didn't understand anything yes David ask me understood Miraculin did you understand beta did you understand the concept of AC generator Miraculin are you there beta
Yeah, sir, I'm here.
so did you understand this thing concept any problem ask me beta
No, sir, I understood.
Okay. Ira, Agatha, Edric, you got this? Okay, now we will learn about DC. Now we will learn about the DC one. Okay.
How do we do that? Well, to build that, first let's get rid of these rings. All right, now to make sure that the current direction remains the same, what we will need is that these brushes to continuously keep changing contacts between these wires for every half a rotation. Let's see why. So if I want the current to flow this way, right now in this position, I can connect this brush to this wire, so the pink side, so that the current flows like this and comes out. But as the coil rotates, notice once it comes to this position, we have seen that the current starts flipping, current reverses. And so now, to maintain the current in the same direction, we would now require this brush to come in contact with this wire. That is the blue side, right? And then again, once we come to this position, again it flips, the current flips, and again we would want now this brush to come in contact with this side. And so as a result, can you see that for every half a rotation, we would want the contacts to keep changing. But how do we make sure that happens automatically? We can do that by attaching split rings. Split rings, as the name suggests, is a ring that is split in between, giving two half rings with some gap in between. Now let's see how this arrangement automatically changes contact for every half a rotation. So right now, this brush is in contact with the pink side. But as the coil rotates and comes to this position, the current reverses, and now notice the brush is in contact with the blue side, making sure the current still flows in the same direction through the bulb. Again, as the coil comes to now this position, finishing another half a rotation, again notice it has changed contact. It is now in contact with the pink ring, connected to the pink side. And this way, we have now built our DC generator, where the current only flows in one direction through any external circuit. And this arrangement, which helps us automatically change contacts, we call them as commutators. So split rings act like commutators. So to summarize what we learned,
Did you understand? The electromagnetic induction is same, but the split rings are there, which makes them to contact with the same shaft so that the current direction don't change. Like inside the coil, which is near the magnetic field, there the current is changing. There the current is reversing. But in this, what they told us that because the split rings are there, so if blue part is connected to that orange one, the yellow one, so when it is moved like this, then that pink one will attach to it so that the current will not change directionally inside the bulb. Did you understand? So there is no much difference in the AC generator or DC generator. In DC generator, simply they use split ring. Otherwise, the concept is same. Okay, the concept is same. The concept is when a coil is moved in the magnetic field lines, it's created the current. That is the main thing. Okay, but what is the difference between the AC generator and DC generator? In AC generator, we are using rings. Okay, and in DC generator, we are using split rings so that when the current will move, the rings will also move, and the direction of the current will not change inside the circuit. Did you understand, guys? Yes or no?
Yes, sir.
Agatha has doubt? Ira, Agatha, any doubt?
So I had one
No.
doubt. Like,
Please.
how does I didn't understand in like the AC current, the bulb keeps changing color. Is it because it has a moment of going to zero, and in the DC generator just continuous current?
Yeah, the DC generate continuous current, but in AC it generated the current which is the like coming zero, then become negative. Then that's why the periodically change. That's why they show the different color. Otherwise, it's not different color. The AC current doesn't show the different color. It's just because they want us to know that because the direction is changing, the color is changing. Otherwise, there's no change in color.
Okay, sir. Understood.
Yeah. Agatha, did you understand?
Yes, sir.
Okay. So, one question now I have in my mind. Let me search for that. Hmm. No, what was I'm searching? Uh, like my question is because we learned that the same coil is there. So we learned that the current is maximum, then zero, then negative maximum, then zero, then positive maximum. Like that we learned. No? So my question is because we are using same DC like AC structure in DC generators, so will the current will come zero in DC generator? That is my question. Like because we know that now the direction is not changing inside the circuit, but the coil is same. So it should be zero in that also in DC. That is my question. I'll search it. I'll search it. AC goes. Did you understand my question, guys? Agatha, Edric.
Yeah.
That is my question.
I thought in DC it never becomes zero.
Well, I remember in the multi-ring there's some gaps, and I realized that that one side will have a gap, while that every time when it becomes like that, it was going too fast for me to notice. But I thought that one side will have that gap, while the other side will have one of those rings. Or the gaps also
Yeah.
electricity.
Basic generator does hit zeros as a coil rotate, but in the negative part of the cycle to positive. You see, while induced voltage in the coil itself dip to zero, the output crash of pulses as zero. Okay. Clip rings in which positive, zero, negative, zero. Perfect. Let's split them with the commutator. Check here. Action positive, pulse, in direction, positive. Pauses briefly at zero. What does this mean? Pauses briefly at zero, then flows forward direction, like series positive. Current does to go to zero or near to zero in DC generator.
Yeah, near to zero.
Output waveform, but it never becomes truly negative in effect. Yeah. So, if we will talk about in DC generators, when they are making DC current, that will go to zero. It means that you will have a chance to leave your hand. There is charge in DC generator. Okay. But if you will take DC batteries, in that there is continuously positively phase direction.
So
There is
DC
no,
battery.
yeah,
So DC battery is dangerous and DC current is okay.
yeah, but we don't have battery more than 12 volt or 24 volts. So it is very safe. But in DC generators, we basically what we need, we need because it is moving like this. There is a position which comes to zero near to the zero, but because again it's moved like this, now the split ring, yeah, split ring is there. That is why the current is going again to the positive, then near to zero, positive, near to zero, positive, near to zero. Like this, the graph form. Did you understand, David? Just on miraculous?
Yes, sir.
Yes, David. Did you understand? Do you have doubt?
No, sir.
Agatha, what about you, beta? You understood? No.
Yeah, I
I mean,
understood.
I am just getting Agatha face in like this in this corner. Again, in this corner like this only. Put it in the right side. Uh, Not little bit more. Okay. So, Agatha, Ayla, did you understand, beta? Yes or no? Okay. So that's the reason because I have also same doubt. Like if it is coming zero, so in DC generator we can come to the zero position. But in DC battery, we are not getting any zero position. We can come near to it, but not to zero. Okay. Okay. So we will now read the DC part. Where is that document? Perfect document. And now I will request Mr. Edric. Please read this. Yeah.
17.7.2 DC generator. This also works like the AC generator. There is just one difference in structure. There is a half rectangular rings rather than ENF rings as seen in AC generators. The rectangular frame rotates and moves from a position parallel to the magnetic field to an upper one. The brush present creates a connection as electric current starts flowing. We can see thus that current flows in the same direction.
Yeah. So split rings are there that we learn that helps us to go in the same direction. So now I told you about AC and DC. So we will read this thing also. Now this is also important. Okay. This is also important part. Yeah. Edric, please.
17.7.3 Alternative current AC and direct current DC. In household as well as industrial purposes, AC is widely used. The current that flows out from the switch points at homes is AC. The current produced by a battery is DC. AC can be changed to DC and vice versa. To change AC to DC, a rectifier is used. AC is transmitted from electricity generation centers to houses and industries through high voltage transformers, step-up transformers at very high voltage. At the site of delivery like houses and industries, the voltage is reduced with the help of step-down transformers. In this way,
So so you know that we have big wires. Uh, Things are there. So basically, there are two types of transformers there. Now, because current has to, like if current is more, then it will travel to a longer distance. We know that if length is increases of the wire, the resistance increases. If less current is there, resistance will stop it in some distance. Hence, the current will not move from one city to another city. Did you understand? Now,
yes,
to make them it, that's why we have big wires and big pillars are there. Electricity poles are there, which have not 220 volts, which we are getting in our houses, which have 11,000 volts. 11,000 volts current is running in that wire, having a good electricity current because the length is more. So if current is very high, then only it can travel to the one city to the another city. Did you understand, guys? No. Okay. Now, because of that, now if that 11,000 volt, if somebody wants to, if somebody wants to have that electricity from 11,000 volts, and if you will put that wire into that the big wire, then the house will burn in the second. Why? Because the 11,000 volt, if it is coming directly to the our houses, our appliances will burst. Even the house will catch fire. The Havels will not help anybody. So for that, like Havels has a tagline, wire that doesn't catch fire. But in that case, the wire will catch fire definitely. Okay. So in that case, we need step down transformer. Now, what is step down for transformer? Like step up increases the voltage, step down decreases the voltage, making to the 220 volts. So near to your house or near to your area, there is one transformer is there. If you will check, this transformer is there, not to your house, but near to the area or in your street. If you're using in street or somewhere else, you will find it out that there is a transformer. Okay, I'll show you. If I believe that it will be there from visible with my mobile. I'll show you where's the trans. I think it's not visible. I'll show you. Just give me a second. So step up transformer is used to increase the voltage so that we can make the electric current to travel from one city to another city. And step down transformer is used in our houses. There are many transformers are there. I believe you can see that. No, it's not visible, no? It's there. Little one is there. There is no option in this of zoom. Yeah, can you see that?
You mean the white building with some poles and a red house in end?
Can you see this? There are cows and all.
Yeah, I can see cows, but I mean a white walls surrounded by some with a red house.
This one.
Yeah, that one.
That one. The pole, two poles are there.
Yeah.
Can you see?
Yes.
That is with
Yes,
transform. If it is not visibly clear there, then you can check this one. Give me a second. Yeah. Can you check this? This one. This one.
Yes,
So
sir.
these transformers bring electricity to your house.
Yeah.
Sure.
Can you see this? The transformer.
Yeah, yes, sir.
Yes, sir.
That is transformer. Okay. And this is our church.
That is a church? Or?
Yeah, that is our church. This is our school. We are in our school.
Pehchan school.
Yeah.
Oh,
So did you understand what I'm trying to say?
yes, sir.
Yeah. So the step down transformer is basically used so that we can reduces the voltage to 220 volt and we can use the current. So if 11,000, like if you will check every appliances, you will find it out that the it is written like 220 volt to 240 volt. Yes. If you will check any appliances that near socket one, you will find it out that appliances can handle 220 or 210 volt to 240 volt. Yes. So that 240 volt, if it is coming like 250 volt, it will come. That appliances will burn. So some fix, like for example, if voltage is down, it happens basically in summer only. So if voltage is down, then what will happen? Mama and Papa will shout and say, "Go turn off the fridge. Go turn off this. Go turn off that." Why? Because if voltage is down, the appliances will not able to handle it. Hence, there is the rest in peace of that appliances.
That means that appliance will have a lunch with.
Jesus. Yeah. Yeah, Agatha. You're saying something.
I don't remember my parents saying that in the summertime, but I remember them saying something like that when there's a thunderstorm.
Wait,
Yeah.
actually, it in thunderstorm, no, it's saying that don't stand under trees or lampposts.
Yeah, that is the reason because current is flowing, electrons are there in the current, hence the electric, like the what to say, um, the thunder in the sky will attract towards the electrons, and then it will pierce you, and it goes to the earth. That's why don't stand under the lamppost. Okay, now second part. Second part, Ira will read. Yes, Ira.
Devices like electric motor that work on AC are stronger than those that use DC. They are also more convenient to use. DC generally used in electrolysis, changing the cells, making electromagnet, etc.
Perfect. And so basically, DC motor is like electric motor that works AC are more stronger based on of DC. So like AC, we have lot of like easy current and easy to make. That's why we are using AC. Third point, please.
DC of same voltage DC of same voltage as AC is more dangerous because in DC direction of flow of current doesn't change. Thus, people coming in contact with DC accidentally get stuck to it, while when they come in contact with AC, due to change in direction of flow of current, they are flung afar. Major
Perfect.
Point 4. Major portion of AC flows through the upper portion of a wire. Thus, where a thick wire has to be installed, several thin wires are coiled together to form a thick wire, which will not the case with DC.
Yeah. So this is all advantages of AC over DC. Okay, so if the question will come, write the AC advantages over DC. So you guys have to write all this. Think the minimum 3 points you can write it down. Did you understand, guys? Agatha, David, Miracle, everyone understood? Okay, so now today's homework is you have to write according to your points. Okay, but make it little 5 marks type question answer. The three question I will give. Okay. First is working principle of AC, working principle of DC, and the AC merit over DC. These three questions are there. Working principle of AC, working principle of DC, and AC merit over DC. These three questions are there. Okay. And like if you will writing working principle of DC, you have to write the whole thing and then AC, then the change in it. Don't say that if it is same like AC. No. Because if different question will come, you are not able to, you are not, you will not write that thing. Okay. So basically, three different questions are there. Yeah.
The last question was
AC merit over DC.
AC merit over DC.
Yeah. So we have these three questions. Did you understand, guys, what I'm trying to say? If the working principle of AC is there and if the question will come, working principle of DC, so you will not write it's the same structure of AC and then the difference will be like, no. You have to write whole thing again. Like whatever the things in happening in AC, you have to write this whole thing again. And then the change in DC, you have to write that. So all these are 5 marks question. Okay, working principle of AC, working principle of DC with a diagram, and AC over the DC. AC merit over DC. Did you understand, guys? This is your homework. So, any problem, David, Miracle, Ira?
No, sir.
Should
No,
I
sir?
write, should I write this homework in the group?
Yes.
Okay.
Okay, then. I hope you enjoyed the class. Till then, bye. Have a nice day. Signing off. Bye bye, Shabakesh. Sayo. Nara. And Ira, please put message in the group that you're not